In this video, we're going to cover section 5.1, where we'll introduce you to stereoisomerism. So stereoisomers, these are compounds that have the same connectivity between atoms, but they differ in the three-dimensional arrangement of those atoms. So we've looked at, up to this point, constitutional isomers, and we said they had the same molecular formula, but different connectivity. Stereoisomers are different in the sense that the molecular formula and the connectivity are the same, but the way they're arranged in three-dimensional space is different. And so isomers can be broken down into constitutional isomers and stereoisomers. And as you'll see in this section, stereoisomers can also be broken down into what we refer to as enantiomers and diastereomers. And we'll talk about the differences between them, but primarily we're going to focus on enantiomers. And these are stereoisomers that have mirror images that cannot be superimposed on one another. And so we'll discuss what we mean by superimposable and non-superimposable shortly. So as an example of stereoisomerism, if we take this ring system, this cycloalkane, cyclohexane, and if we place two substituents on that ring, that gives rise to what we can refer to as stereoisomerism, that we could have both of these methyl groups on the same side of the ring, or we could have one methyl group, let's say, above the ring, and the second group below the ring. Remember that these ring systems, although there's conformational flexibility, we cannot invert any carbon at any one point in time. We would need to break a bond in order to allow this methyl group to rotate below the ring. So these are different compounds. These are named differently, and the only distinction that we provide in the name is the use of the terms cis and trans. And so specifically, the term cis is used to signify that the two groups are on the same side of the ring, same side meaning the plane of the ring system, while the term trans signifies that the two groups are on opposite sides of the ring. So the structure on the left would be a cis, which is italicized, cis hyphen 1, 2 hyphen dimethyl cyclohexane. And the structure on the right, the only difference is that the stereo descriptor in front, we would use trans to identify that those two methyl groups are on opposite sides of the ring. So that's a trans 1,2 dimethyl cyclohexane. So these are stereoisomers. These are the two possible stereoisomers for 1,2 dimethyl cyclohexane. We have the cis isomer and the trans isomer. In fact, these cis-trans isomers are referred to as diastereomers, and that these stereoisomers are non-superimposable, but not mirror images of one another. And we'll discuss this a little bit more, what we mean by superimposable and mirror image, in just a moment. So as we said, the terms cis and trans are used to describe this stereoisomerism, and it can be used not just with ring systems, but we can also use that for di-substituted alkenes. So when we have these two methyl groups on the same side of the double bond, we refer to this as cis. If the two groups are on opposite sides of the double bond, in the sense that if I were to draw a line with my pen from one group to the other, if I cross that double bond, then that is considered a trans isomer. So the cis-2-butene, the trans-2-butene, diastereomers like this have different properties. So you can see that the boiling points of these two compounds, they're similar, but they're not exactly the same. Whereas enantiomers have the same physical properties. So let's look at what we mean by superimposable. So if an object is identical to its mirror image, the object and its mirror image are said to be superimposable. So we could take this image of these glasses, rotate it by 180 degrees, and place it directly over top. And every aspect of those glasses would match with its mirror image. Whereas in this structure here, if we were to take the same pair of glasses now with one of the lenses popped out, if you will, if we were to rotate this by 180 degrees and try to place it on top of this, we would find that the lenses would not line up. So if you have an object that is not superimposable on its mirror image, then we consider that object chiral. And so we'll assign chirality to organic compounds in a similar way. So for a molecule to be considered chiral, it must contain at least one chirality center. And a chirality center is a tetrahedral carbon atom, so an sp3 hybridized carbon, that bears 4 different groups. So the neighboring atoms attached to that tetrahedral carbon will be different. So you can see in this cartoonish picture of a tetrahedral, here's our carbon atom, and what's attached to it are designated in different colors, 4 different groups. And so if this particular structure, if you were to place a mirror in front of it, or if you had the mirror image as a molecule of this particular compound, we would say that both of these compounds are chiral in that we can't take this structure and rotate it in any way in which all 4 groups are going to overlap. If we were to rotate this by 180 degrees, yes, we could overlap the blue and the red groups attached to this chiral center, but there'd be a mismatch between the white and the green. And so by definition, if you have a carbon atom with 4 different groups attached to it, we consider that a chirality center and the molecule as being chiral. So let's look at an example of an organic compound that's chiral. So if we look at 2-butanol, let's draw its structure. Here's the line bond structure for 2-butanol. Now, if we were to draw a tetrahedral around this particular position, and I'll use that asterisk to show the chirality center in this molecule. If we were to draw our tetrahedral, we draw 2 bonds in the plane, 1 bond coming out at you and 1 bond in behind. And if we were to attach the 4 groups of this particular carbon center, we would have a OH group, so I'll highlight that. We have an OH group attached to our chirality center. We have a methyl group. We have an ethyl group. And what's not being shown is the hydrogen also attached to that carbon. And so that represents the 4 different groups. We have a hydroxyl group, an ethyl group, and a methyl group, as well as a hydrogen attached to that chirality center, that carbon. Now, if we were to redraw the mirror image of it, we can see that we would place our 2 bonds in the plane towards the other 2, if you will, or parallel. And again, our ethyl group would be in back, our methyl group is coming in towards us. These are considered the 2 enantiomers of 2-butanol. And we'll show you how we identify what stereo descriptor we use to identify the differences when we're naming 2-butanol. We'll show that in the next video. So here's some examples of some chiral compounds. And what's highlighted in green are the chirality centers within these molecules. And so we can see in our first example, to this carbon, we have a chlorine atom, a methyl group, and an ethyl group, and what's not being shown in the bond line structure is a hydrogen. Similarly, in this alcohol, we have the hydroxyl group, an ethyl group, and a 3-carbon group, propyl, as well as a hydrogen not being shown. So these carbons are considered chirality centers, unlike the other carbons in this system. This carbon here is attached to 3 hydrogens, and so those 3 hydrogens being identical, that would ensure that this cannot be a chirality center. Now in the last compound, we have a chiral center, chirality center, because this carbon atom is not only attached to a bromine atom and a hydrogen that's not being shown, but the path is different if you go clockwise versus counterclockwise. So we're just going to be comparing the first atom attached to that chirality center and what's attached to it. So this carbon has a hydrogen and a double bond to another carbon, whereas this carbon has two hydrogens and a carbon attached to it. So the nature of the groups, if you will, attached to the neighboring carbon are different, and that, in a sense, is a different group. So that would give rise to this carbon being a chirality center because there are 4 different groups attached to it. And this is very common in a lot of natural compounds, that we have many, many chiral centers. You'll see that molecules like cholesterol have upwards, I believe, of 16 chirality centers. And so there's many different, actually 2 to the n, stereoisomers associated with these biological compounds. Now, the term we use to describe these pairs, we refer to these as enantiomers. So we saw previously that stereoisomers can be enantiomers or diastereomers. Diastereomers are not mirror images of one another, whereas enantiomers are mirror images of one another. So both are not superimposable, non-superimposable, but the enantiomers specifically are mirror images of one another, whereas the cis-trans isomer examples we saw previously, these were not mirror images of each other, nor were they superimposable. So enantiomers are stereoisomers, and they're non-superimposable mirror images of one another. And so again, we could look at the structure rotated, and we could overlap at any one point 2 of the groups, but not the other 2 groups. And so these compounds are both chiral, and they are considered a pair in the sense that they are mirror images of one another. So we refer to this set of compounds as being enantiomers. So a chiral compound with a single chirality center will have exactly 1 enantiomer. And so chiral compounds exist as a pair of enantiomers. Now, this is very common, like I said, in nature. And what's very interesting about chirality is that our noses, the olfactory receptors in the nose, those receptors are chiral. And so the way that they interact with odors, aromatic compounds, is very important to our recognition of the smell of various things as we go about our day. So a specific compound will bind to a number of different receptors in our nose. Now, the binding may not be perfect, but our brain is able to translate patterns, how a particular odorous molecule will interact with a variety of receptors will be remembered as a certain scent. So there may well be over 10,000 different odors present in our everyday life, but we don't have specific receptors for each scent. It's basically a pattern recognition that there's various receptors that will bind weakly or more strongly to various odorous molecules, and it's the pattern of those binding events as a whole that gives rise to, a memory of that odor. And so we can recognize scent based on this pattern recognition. So that's pretty interesting in my opinion. So normally if we were in an in-class face-to-face setting, I'd be handing around some vials containing the compounds shown on this slide. So carvone, there are 2 enantiomers to carvone, and we're going to describe in the next video how we assign S and R. These are the stereo descriptors that we'll use for enantiomers. But carvone, the S-carvone, smells like caraway seeds. So if you're a fan of Indian food, you've smelled caraway before. It's a very fragrant, very, very nice odor and makes that food oh so good. But the other enantiomer, very different scent. The R-carvone smells like mint, smells like spearmint. And so when you look at the structures of these two compounds, they are identical in every way except for how these two substituents are placed in three-dimensional space. So the S-carvone, if we look at the plane and look from this perspective, that hydrogen is above the plane and this alkenyl substituent is below the plane. That is our S-carvone. Whereas if we just switch the placement of those two groups, placing the hydrogen below and that alkenyl substituent above, that gives it rise to our mirror image, the other enantiomer, the R-carvone. And the way those two molecules interact with our olfactory receptors are quite different. And so our brain is able to recognize that particular pattern that the interaction of these two compounds make with those various receptors. In another example, limonene is what gives rise to the odor that we find with lemons and oranges. And again, I would normally hand these around the room for you to take a sniff to see if you can distinguish between lemons and oranges. Not all of us have great olfactory receptors, or at least that recognition. I think the best of us end up working in the food industry as chefs. But nonetheless, if you were to slice open a lemon and an orange, there's obviously some distinct odors associated with that. One of those compounds that gives rise to the smell of these particular fruits is limonene. And so the R enantiomer is associated with oranges and the S enantiomer is associated with lemons. So let's look at a chiral molecule and identify the chirality center and then draw the enantiomer for it. So in this example, we're looking at adrenaline as shown. And so again, the definition of a chirality center is a carbon atom that is sp3 hybridized or tetrahedral, and it has 4 different groups attached to it. And so typically, or more than typically, as always, these chirality centers will be three-dimensional. So there'll be three-dimensional bonds drawn around the chirality center. You can have a chirality center that's not explicitly shown with three-dimensional bonds. All that can tell you is that you have both possibilities. You can't identify whether you have an R or an S enantiomer, the two different enantiomers of a particular pair, if you're not given the three-dimensional information. So in this question, or this example, we do see a carbon center that has three-dimensional bonds to it. And so if we check this particular carbon, we have a hydroxyl group, we have all this part of the molecule, it's sort of an amine structure, and then we have this ring system, this phenyl system substituted. And so those are 4 different groups. There's also, of course, a hydrogen attached to this carbon. You always got to remember that if you see a carbon with 3 bonds to it, what's not being drawn in is that 4th bond to hydrogen. So this is a chirality center, and so this structure does represent one enantiomer of a pair. So if we were to redraw this structure, the simplest way to redraw the other enantiomer is to draw everything else in the same way as shown, and to only change the nature of the three-dimensional bond at that chirality center. So instead of showing this hydroxyl group coming towards you, if we show that hydroxyl group going away from us, that is going to represent the other enantiomer in this pair. So I'll use my hashed wedge to represent the bond going away, and our hydroxyl group now is behind the plane as opposed to above the plane. And so this represents the other enantiomer, the mirror image of our original adrenaline structure. And again, this has the same structure as what was shown for adrenaline, but may interact differently in the body due to the difference in the stereochemistry, the three-dimensionality specifically around this particular carbon center. So if you have any questions about identifying chirality centers in organic structures, which is the prerequisite for a molecule being chiral, by all means, send me an email, or we can set up a Zoom appointment, or hopefully at some point, we'll have some discussion in our forum. Thank you.